everyone. Thank you so much for joining us back in this room for our power talks. Same deal as yesterday. We're going to go through a number of these very interesting flash talks to help you get a sense of what's going on these days. So first, I would like to welcome to the stage Liam Buckley. On deck is Shannenia Sumawan.
Hi everyone, I'm Liam from IES. The only thing better than an energy storage system is passive energy storage. So what I'm discussing are different types of energy storage, relevant hierarchy of model data, phase change materials and ceiling tiles, and some lessons learned. So I'm sure everyone's familiar with at least two types of energy storage, electric battery storage and thermal energy storage, water in a tank. But the third type of energy storage that is often underutilized is the building itself. Whereby the thermal mass is utilized to both accept, absorb, store, and release heat on its own due to the structure of the building. And there are two important concepts associated with the thermal mass in our 3D models. Number one, that's most important, is you have to use the Asher heat balance method in order to capture the physics. One part of that is you must model each surface of the building and space. And the second critical part is that you must account for radiation and convection with a time delay, and all of that encompasses the thermal mass. How that relates to the 3D model, if I pull up the data hierarchy, so we'll start off with a zone that might be a grandparent, then a room might be a child, and we'll have surfaces as a grandchild. And belonging to the surfaces, you might have things like walls or glazing, holes, doors, and so forth. Introducing a fourth one, though, would be an other opaque surface type. And that could be used for things like thermal bridging, ceiling tiles, which is what I'm discussing today, and or radiant panels in the future. So bringing that to a real world concept with Armstrong, they are the leader in design and manufacture of ceiling and wall system solutions. Been around for 160 years. They have, there's lots of these, but them as an example have a product called Templock, which adds a phase change material to the back of the ceiling tile or the top of the ceiling tile. And what it does is it passively regulates the room temperature by releasing and absorbing sufficient energy at phase transition. What I mean by at phase transition is it's basically changing from solid state to liquid state right when you need it to, when your space set point temperature is changing. So here's a photograph on the left-hand side of the lab chamber condition that was tested with real-world conditions and calibrated against the Apache simulation engine, and they are in strong agreement on the results that it shows. So an example model, I'll use the large office prototype, put it in LA. This is a Title 24 compliance model, both with and without the PCM tile, covering 90% of the ceiling spaces. So the energy results will show a 10% better energy saving on the heating side, 4.5% better energy saving on the cooling side. You get similar results on carbon emissions, and then in the lower left-hand corner, you'll see a little snapshot from the Perf1 compliance report showing you a 7.5% better saving in the source energy condition just by adding this passive phase change material. So some quick lessons learned. This is an exploded model showing the ceiling plenums from the spaces below. If you focus on the center zone and the one on the right-hand side, the one on the right-hand side is showing individual ceiling tiles modeled. The one in the center is just doing 100% tile area. They give you the same results. So no need to model each individual ceiling tile. You can just say 80%, 90% of ceiling tile, and that will give you the same results. The second lesson learned is you must account for hourly and even sub-hourly analyses. So this technology works really well during the hourly condition. You'll also get benefits on things like operative temperature, right when the building is becoming occupied or unoccupied. The best energy metrics you'll see will be when you account for hourly source factors, hourly carbon emission factors, or something like LSC in the future. And before I get asked, yes, you can use this for Title 24 compliance. There's nothing in the ACM that regulates ceilings or ceiling materials. There's no section there. Even if there were, there's nothing that's going to regulate heat transfer within a zone. So really what I'm saying there is, so long as you apply a ceiling tile with a PCM in the same zone, that complies with requirements in California. But what I mean by the same zone is at least one space and at least one ceiling plenum above. And that's all you'll need to model this technology. Thank you for your time.
Thanks, Liam. Yep, come on up, Shannon.
Good afternoon, everyone. My name is Shannon. I'm with TRC Companies. So it's a pleasure to be here today, and I will be presenting on the critical role of building energy modeling in rich code development as well as cost-effective analysis. So before I kind of like go into the detail about the main slide, I want to ask you how many of you here have heard or are familiar with rich code? Oh, nice. So yeah, I just want to make sure that everyone is on the same page. So I'll kind of like briefly go over the rich code overview. So first, what is rich code? Rich code is a local amendment to the California Building Code, or what we commonly known as Title 24. And this means that local governments have the authority to adopt amendments to Title 24 that go beyond the minimum state requirements. And these amendments is what we call rich code, because like you kind of like reach beyond of what what is the state require, or like the baseline standards. And there are two types of rich code. So the first one is prescriptive, and the other one is performance. And second question here: why should one adopt a rich code? So adopting rich code kind of like allows your local government or jurisdictions to kind of like take meaningful steps toward their climate and energy goals. So by setting standards that kind of like go beyond the minimum state requirements, rich code can help communities achieve like greater energy efficiency, cost savings, as well as emissions reductions. So they can also serve as powerful tools. Here I have listed like climate action plan, energy plan, and policy goals. So this can be done by ensuring that new development are built to a higher performance standards from the start. And in the long run, these higher standards not only deliver like immediate and cost savings, but also create like compounding benefits for the communities through lower energy bills, as well as more resilient building design. So what is the process of adopting rich code? We first usually start with engaging local community and then stakeholders as well as building officials. And then second, we have to obtain the cost effectiveness study. So a rich code, it has to be cost effective in order to get implemented. And then third, we submit the rich code for city council for review or vote. And lastly, we submit the adopted rich code for CEC approval and filing with the BSC. So BSC stands for Building Standards Commissions. So lastly, why is BEM important in rich code? So building energy modeling plays a critical role in developing effective rich codes. So it provides like the analytical foundations needed to design and evaluate different energy efficiency measures or measure packages, and also to quantify the trade-off between the upfront costs as well as the long-term operational energy savings. So I want to illustrate this further. TRC does a lot of different rich code projects, but for this presentation, I'll use one of the example here. So this is the latest rich code project that were published in July. And this is kind of like focusing on the 2025 non-residential alterations and the transition from single zone AC unit to single zone heat pump units. I won't go too much into the specifics on the modeling because we already have the webinar back in June, which you can easily access through the local Energy Code Ace website. And if you email me, I can also happy to point you out to the website. So for the scope, I'll actually put everything here. For the scope, the 2025 code language actually serves as the foundation of this study. So the initial requirement requires that all single zone RTU unit with cooling capacity below 65 to be a single zone heat pump. So this presents some rich code opportunities to kind of like increase the requirement from like below 5 ton essentially to like 5 to 20 ton. So for the methodology, we are using CBECC 2025. And we collect like cost data from equipment manufacturers as well as mechanical contractors to evaluate the cost effectiveness and technical feasibility of the retrofit. So here I want to kind of like look more on how BEM support this development. So in building energy modeling, it is like This is kind of like the foundation to establish the cost effectiveness because like we are using two key outputs from CBECC. The first one is the hourly result, or what we commonly known as 8760, which is used to calculate the on-bill savings. And then the second output is the annual result to calculate the LSC. So yesterday we already have a very in-depth presentation on the LSC. So I just want to kind of like recap this for the on-bill savings that we kind of like analyze. It's mostly focusing on the life cycle of the customer-focused like life cycle cost approach. So where we value energy based on the estimated site energy use, as well as customer utility bill savings. So we kind of like take into account on the discount rate and escalation rate. For the LSC, formerly known as TDV, we pretty much use this to kind of like understand the savings using the factors, the electric and natural gas factors, projected over 30 building year lifetime. So for overall BEM here, So the key takeaway here is that BEM is more than a compliance and analytical tool, so it is serving as the foundation for designing cost-effective data-driven reach code. So yeah, thank you.
Thanks, Shannon. Come on up, Luke Morton, and on deck is Nick Brown.
All right, hi, my name is Luke Morton. My presentation today, compliance, conservation, and code using BEM for market transformation. This is probably like a super Department of Obvious review, but they had me come up with this slide deck. So I'm gonna recap kind of the world as it looks from my perspective. Okay, why we're all here, energy efficiency is the biggest no-brainer of all time. So this is our syllogism for how we get here. And given that numerous market failures and negative externalities exist for why energy efficiency isn't deployed, therefore we have regulatory intervention. Now here's your standard market transformation curve. I want to point out the, code readiness, kind of early adopters on the lower end of the curve. There's performance options out there. Then we scale up, we adopt these measures as prescriptive, and there's more market transformation, things are going awesome, and then at some point the market is transformed, then we transition maybe into a mandatory adoption phase. And here's our typical framework. We've seen a lot of this before. I just wanted to add here that my framework for this, mandatory requirements, mature technologies always make sense in all cases. Prescriptive measures are more of that frontier for market transformation, ready for scaling. Sometimes make sense, but we then have performance trade-offs for when they don't make sense in the field. Okay, moving on. I wanted to give a shout out to all the market transformation activities. This is not an exhaustive list, but for the activities that are out there in the California market and beyond. Before I get to the question mark, programs for code compliance, right? The ship sails, leaves the harbor of market transformation programs, early adopters. And then we get into who implements it in the real world and that steep part of the curve. I'm gonna call these the market transformation gnomes. You guys might know where this is coming from, but here's your market transformation gnomes framework. Phase 1, prescribed measures. Phase 2, something. Phase 3, market transformation, success. No, but in reality, we're all here because really it is the BEM world that is implementing this. I'm shouting out to my CBECC and IBIPSA colleagues out here. We're the ones herding cats, and what does this look like? Energy efficiency, here's our 3 tenets. Efficiency is an optimization, BEM is evaluation of trade-offs. The key point, energy code compliance is a negotiation. Here's your perfect project cycle. Ideal compliance, 100% CDs, everything's perfect on the drawings, compliance achieved, paperwork done. The plan check, they build what's on the drawings, everything's perfect, inspection, and you get your C of O. Here's what the real world looks like in a great project. You'll see words like Rumsfeldian epistemology and WAGs. You can ask me about those later. But it's a series of negotiations, and this is on a great project. 2 gambits. Negotiating compliance is because it's a necessary idea. Negotiate a measure because it's bad plural here on this slide. It's a good idea that we're trying to deliver value for our clients. Challenges to the storytelling. First, obviously, is this tension between a cost effectiveness, LSC, versus on-bill. This is something we explore a lot, but where there are gaps there, that's a challenge. Sometimes it presents challenges for how we negotiate these measures. I'm going to briefly shout out to a bunch of these other challenges that we talk about in our meetings. We're the Sisyphean rolling this boulder up the hill. Okay, wanted to shift a big challenge. 10 things I hate about AB 130, all right. Because this is a story, transitioning to challenges in storytelling. Number one, we talked about how energy efficiency is the biggest no-brainer of all time. Pausing the energy code is the biggest, dumbest thing to do because it stops the CEC and our regulatory authorities from promulgating measures which lower housing costs, right? Duh. But vibes, where there's also lots of vibes out there, and I know my colleagues were like, yeah, some of this stuff just looks good on paper, and that's about it. And it's really challenging to negotiate some of these measures in the field because the reality is just fundamentally different. And that vibe is getting translated in the world. A couple more slides. Step two, that leads me to say that what if AB 30, the vibes behind what AB 130 are not wrong? Which leads me to the response. The market responds to code, and some of those responses about how does the code learn from the marketplace? Can we reconcile if there's misalignments, mismatches in the cost effectiveness and in the overall compliance framework? How do we fix those? Too many, I see ratchets up there, vices, too many people perceive code as a weapon of math obstruction. How do we convince them that it's a tool for mass construction? And slide. Okay, thanks guys.
That was a feat. Up next, Nick Brown, on deck, Afshin Faramarzi.
Rumsfeld. All right, I've been asked to speak on behalf of Energy Code ACE. I'm Nick Brown, one of the instructors. I remember where I was when I first heard about electrification. It was 2019. I was at the CBECC conference, and there was a CPUC speaker who blew my mind with that. Many in this room probably heard about electrification a year or two before that, but it changed everything for us at Energy Code ACE. We developed a bunch of really good classes and resources that treated electricity and gas even-handedly. And we were told to train that they were equally valid ways of powering buildings. In fact, we were told not to deviate from that script in no uncertain terms. So under the leadership of Jill Marver, who's a fantastic boss for this program, by the way, shout out, sets a great example and makes sure that we achieve great things, and this is a high-performing team as a result of her. And she had the good foresight to add Dave Vintner a few years after that. And he's brought this focus, I think, on electrification and decarbonization, and it helped us update the energy code offerings for this time. So our fact sheets now treat these topics like how to design single-family homes that run on clean energy. It goes into these once taboo areas of, hey, our grid's changing and electric buildings are far preferable to the old mixed fuel ones we used to build. Fact sheets on electric readiness, which we all know are a strong nudge, policy nudge towards the electric design as much as the prescriptive standards are. We've got recent additions to Energy Code ACE trainings, including the code breaker sessions, which are designed to be 1 hour, get in, get out, good for ASHRAE meetings and AIA, monthly meetings on topics like talking with clients about electrification. We've got one on embodied carbon and CalGreen, and we've got a series for all occupancies on the all-electric provisions, prescriptive standards for heat pumps and heat pump water heaters, in much of the code now, electric readiness, et cetera. And like all the Energy Code ACE instructors, we like to weave in our real-world experience to bring the content to life. Here's a slide from talking with clients about electrification, where we show people the total energy cost in the form of a burden. I think we were talking about an energy burden earlier this morning. What percent of average median income is going towards energy when you consider not just the energy use of your home, but transportation, and now the convenience of being able to charge that EV with the same electrical system is a wonderful perk. And it's a very compelling slide, and maybe in a way that people haven't seen before. In my case, based on my own experience electrifying my home and transportation. And then we show slides like this, where we show the impact on utility costs, even with NEM 3 taken into account, of electrifying. And you notice those utility costs don't go down electrifying alone until you pair it with solar and or a battery. But look at the greenhouse gas emission differences, which is why that 2019 presentation blew my mind. That was something we weren't talking a lot about in our circles until then. So encourage you to check out those offerings at energycodeace.com, as many in the industry already are. Nice to see when we present, we're pretty well woven into the fabric of this industry by now. Tools, training, and resources. I don't have time to highlight them, but I will show off our nice graphics. Thanks very much.
Thanks, Nick. Up next, Afshin Faramarzi, and on deck, I forget, it's on the agenda. Ooh, Rob Guglielmetti.
Hello everyone, my name is Afshin, and today I'm going to talk about the air source heat pump, indirect coverage, and right sizing while maintaining thermal comfort. The question here is that can be reduced upfront cost by downsizing the air source heat pump or reducing the indoor unit. Our research shows yes. Actually, there was a field study in New York where homeowners downsized their heat pump to 80% of the design load, but remain comfortable even in the colder climate. So we wanted to actually evaluate these can be applied for the California climate zones. We did parametric simulation with Energy Plus. We actually created a typical single family and multifamily models in Design Builder in California, and exported the IDF, Energy Plus IDF file. And at the same time, we modeled the manual S to calculate the load and right sizing the heat pump with manual J. So with having the IDF and the heat pump size, we parameterized the IDF file compatible with the model kit framework, and we run parametric simulation. And with having the output of the parametric simulation, we analyzed the thermal comfort analysis with the Python script. So there were too many scenarios that we considered: 2 building type, single family, multifamily, 16 climate zone of California, 4 main orientation, and 4 multifamily adjacency, 3 vintages, and with 3 configuration. Baseline means that the standard design. Indirect coverage, that we are reducing the indoor head unit in actually in zones, and suitable capacity is downsizing the capacity of heat pump to 80% with 2 ducting scenario, ductless and ducted, and 2 airflow. So this graph shows actually the thermal comfort analysis for suitable capacity. The left figure shows for ductless and the right for ducted. The y-axis shows the percentage of the hours that the PMV is between plus or minus 5. So you can see in both scenarios, the box plot of baseline and suitable capacity is very close to each other. Mean, median, or even quartile is very close, meaning that the suitable capacity is providing the thermal comfort to occupants. But the scenario changes the indirect coverage. For the ductless and ducted, we don't have too much comfort based on the research that we did. But being flexible on the threshold, instead of 0.5, we increase it to 0.7, or closing level adjustment, we reach a level of relative comfort in the environment. So to wrap up, suitable capacity air source heat pump provide the similar comfort to full-size systems across California climate zone with 600 to 1,500 savings in upfront cost. Indirect coverage lower the first cost by reducing the condition zone, but we have a potential comfort impact in unconditioned space. But we can improve the condition with clothing adjustment, especially in winter, and also using transfer fans. So recommendation, we can consider downsizing air source heat pump to 80% of the design load, but further research needs to assess the long-term energy and also maintenance cost. So I would like to mention this was the CalNIX study funded by the IOUs. Yeah, thank you so much.
Awesome. Thank you, Afshin. Next, Rob Guglielmetti. And Russ King is the last Power Talk.
Crushed it that time. Thanks. Hey, everybody. I'm Rob Guglielmetti. She got the pronunciation spot on that time. Appreciate it. Yeah, and thanks everybody for being here, and thanks to SCE for putting this on. And somebody, I forget who it was on the panel this morning, said when they closed something about like thanking this, like we were addressed as a family. And I really appreciate that, and I really feel that, because I do feel like this is a really collegial, kind of familial group of really smart people, and it's really a pleasure to get for giving me the 5 to talk to you guys today about this project that we've been working on for a couple years now, and it's been known as the GitHub migration, or GitHub project. Basically what we've been doing and what we're nearly complete with doing is migrating the source code for CBECC from an older source code management versioning system known as, SVN really, which is hosted on an old website called SourceForge, to Git and GitHub. And so I just want to talk really quick about the goals for this project, the current status of the project, and kind of like future to-dos. So yeah, again, the idea here was to move all the source code to what is really kind of like the gold standard for managing software projects today, which is Git and GitHub. By moving all the source code to GitHub, it's just a completely different, much more modern infrastructure for managing software projects, and it gives us a lot of capabilities that we didn't really have on the old system, and that goes to developers, but also to end users. The goals were, again, to like modernize the way we do the project, the way we deliver software, the way you guys interact with the software, and just generally improve software delivery. So what does that look like? I mean, what does that mean? It's like better testing of the software, more automation as part of the whole software delivery process and management process, so that we have more time to do more stuff and receive more stuff from you guys and integrate it. With that, also the CEC really wanted to have a private repository for managing all the tickets, issues, whatever you want to call them. But obviously still maintain that it's an open source software product, so to maintain that public-facing repository as well. So in terms of status, so as of August of this year, the source code has been migrated to, has been migrated to GitHub. And the dev team is basically like living in that world now instead of SourceForge. And what that looked like was we had to migrate, because we didn't want to just like start over, right? Just like copy all the source code over to a GitHub repository and then just continue on as if, right? There's a lot of history, 10 years worth plus of development history, bug fixes, new new developments, documentation, you name it, right? Still living on the old system. It was on the order of 9,000 commits, I think it was, when we were ready to flip the switch. So there was some there was some code merging and blending, right? As we talked about, Nikhil mentioned it, others mentioned it over the course of the last day and a half. The CBECC res is now sort of blended. The source code is mixed with CBECC. So that all happened right before we flipped the switch, right before we migrated over. And we had an opportunity to sort of condense, and there's now 2,000 commits on the new system, and just a few branches. There was double-digit branches, many of which were stale at this point on the old system. So this was a great opportunity to just kind of like, clean out, sweep out, do a little inventory, and just migrate what we really needed. And that's been done. We have a public mirror. Anytime the developers commit something to the private repo, it's automatically mirrored over to the public side, like as soon as it's merged to main. So that's just sort of like automated and ongoing. We also have a user support repository. It's a private repo, but so the way the dev team still gets user support questions and requests is through the email, but they're immediately turned into issues and tickets on a separate GitHub repository. So everything is now like much better integrated. And 0 minutes remaining. So real quick, we want to start posting the releases on the GitHub site. This is something I've been trying to force the issue on. Documentation, user support, it's all right there. It'll be in the thing. Here she comes. I'm out of here. Thanks, you guys.
Thank you, Rob. Russell King, please welcome to the stage.
Okay, so using video game graphics and scanning technology to capture building geometry. My name is Russ King. The company is Coded Energy. We're the developers of Quick Model 3D software. And our software is written in Unity. It's a video game platform. It's 3D. The 3D LiDAR scanning app that we use is called Polycam. It's an off-the-shelf LiDAR app that you can buy in the Apple Store. And another app that we use is called CBECC. It works on any phone. We even have homeowners scanning their houses, and they'll send us a floor plan of their house from the scan. So it works really well on existing homes. Okay, so this is a quick model. You can import any image file, PDF, JPEG, anything of the floor plan. The floor plan that and I'm a little nervous to change screens here, but the floor plan that we're trying to do is this house right here, okay? So the idea is, the task is to get this information into the software as quickly and easily as possible. So you import the floor plan, and basically you just cover it with squares like this. Now this isn't too terribly impressive, but you can kind of get an idea. You're just covering this place up, and I'm going to do this in a room by room takeoff, because we do this for HVAC design, and if you're designing ducts, you need to do this on a room by room basis. So you just place these boxes. It's very easy to do. If you're into Minecraft, it's kind of the same thing, or Tetris. And then you can designate different areas. This is the garage. So I'm going to call this unconditioned garage, and you'll see that it's a different color, but you get the idea. So what you're actually doing, and it looks like it's just boxes, but what it really is, if I take it out of 2D mode, what I've really done is created a 3D model. Okay, and what it's doing is it's taking all that information and it's putting into tables. It's tabulating floor areas, wall areas, window areas, ceiling areas, everything is going into these data tabs, these data tables up here. So there's all the walls. Let me show you this house finished. Here is the finished product which you can draw your ducts on in 3D. But this can also export into CBECC Res. We have a version that exports into Energy Gauge USA. Okay, so that's if you have a set of plans. If you have an existing house, what you'll do is you'll scan it with a LiDAR scan. This is a house, it took me about 15 minutes to scan this house, and it'll save an OBJ file. Oops. Didn't think about the mouse issues here. And we can import, if I can see that, an OBJ file straight into our software. Oops, hold on. Sorry. And you must, yes, you shall, please. And it will open that same house in 3D. And it'll do all the same things. It tabulates all the data, puts it in tables. It can export in all different kinds of formats. And then let me just show you an example of the CBECC file. This is a phone app that works on any phone. You start in one corner of the house and you walk through the entire house, basically pointed at your baseboards. You get back, you send that file off, and they send you back a floor plan that looks like this for free. So it's great software. We can import that floor plan and build the house out of boxes. Thank you.